Holmes and Watson are two detectives. They are working on a criminal case at the priory school. They found a bicycle track on the road covered with snow in front of the priory school. Looking at the path of bicycle traced on the road covered with snow, Holmes immediately understood which way the bicycle went. Watson was confused and he asked, "How did you determine which way the bicycle went just looking towards this path?" So, in the left figure, given this bicycle path, although it is extended in both the directions, but we are looking at some segment of this extended bicycle path in both the direction. And looking at this segment, we have to determine which way the bicycle went. So for that, we need to understand the mechanics of bicycles. First, the bicycle's back tire always move in a direction pointing towards the front wheel's point of contact with the ground and not the point where the front wheel was. And this is due to the structure of the bicycle. The frame, back wheel, and the point of contact of the front wheel of the bicycle are all along the same direction. But the direction of motion of front wheel is not the same because it is free to rotate about this frame, whereas the back wheel and frame are connected. This property has an important application. Let us assume for some time that the track 1 is of back wheel and the track 2 is of front wheel. If you choose any arbitrary point A on the back wheel track, then the direction of motion of the bicycle at this point A will be along the tangent to this back wheel track at point A. So if we draw a tangent at point A to the back wheel track, it will intersect the front wheel track at point B. This point B is the position of front wheel at the time when the back wheel is at A. Because at point A, the bicycle is moving towards the tangent to point A, and also we know from the property 1 we have discussed that the bicycle always moves in a direction pointing towards the front wheel's point of contact. And since we are given the front wheel track, the position of the front wheel will be exactly at B. If we haven't been given the front wheel track, then the position of front wheel can be anywhere along this tangent to the point A. But we have been given the front wheel track, so the point at which this tangent intersect the front wheel track, which is the B, will be the position of front wheel, and the length of the bicycle will be AB. Now the property 2. The distance between the points of contact of the front wheel and the back wheel is always constant because it is the length of the bicycle, which was AB in the previous case we have seen. Now, knowing these two properties, we are able to find the solution of the actual problem. Solution. Step 1. First, we have to identify which is the front wheel path and which is the back wheel path. A simple way to do this is the path which is having lesser variation is the back wheel path, and the path which is having more variation is the front wheel path. The front wheel path always encloses the back wheel path with its larger amplitude. Hence, by simple observation, we can also identify which path is due to which wheel. However, I will give the actual method to find which path is of back wheel and which is of the front wheel. Step 2. Draw tangents from any point on the back wheel in the directions. Repeat this process for a few points on the back wheel track, and the direction which is giving the constant length of bicycle in all the cases is the direction of motion of the bicycle. In the figure shown, we have taken 2 points A and B on the back wheel track. The tangents drawn in black color, which are the tangents drawn in the right directions, are giving constant length of bicycle, whereas the tangents drawn in left direction, which are shown in red color, do not give constant length of bicycle. The length of the bicycle, as we have discussed, is the point on the back wheel track on which we draw the tangent and the point on the front wheel track at which this tangent intersects. And since the tangents drawn in right direction give constant length
and as we know, the length of the bicycle must be constant throughout the motion of the bicycle. So the direction giving the constant length of these tangents is the direction of motion of the bicycle. In this particular case, it is the right. Hence, in this way, Holmes identified which way the bicycle went. The alternate way to do the step 1 is to draw the tangents in both the path in both the directions. If we have chosen back wheel path, then tangents drawn in either direction will give constant length of bicycle. But if we have chosen the front wheel path, then tangents drawn in both the directions will not give the constant length of bicycle, and hence you can identify both direction in which bicycle had gone and which is the front wheel and which is the back wheel path of the bicycle. Now we are discussing two miscellaneous cases. Case 1. When the tangents drawn in both the directions are not giving an equal length of the bicycle, and the given track is not of bicycle but it is of two unicycles. So it is not possible to construct a path in which the length of bicycle is not constant. It is indeed the path of two unicycles, because in that case there is no such constraint of length of bicycle to be constant. Now case 2. When tangents drawn in both the directions are giving an equal length of bicycle, then the front wheel and back wheel paths are concentric circles satisfying the equation L square plus small r square equal to capital R square, where small r and capital R are radii of front wheel and back wheel path and are shown in the figure as blue circle and red outer circle respectively, and L is the length of bicycle. In this case, as we can see, so in this figure, triangle OCA and triangle OCB are congruent, so AC and CB are equal. Furthermore, AB and DE are also equal. From the same logic, we can say DF and FE are also equal. So all the segments CB, CA, FD and FE are equal. So the tangents drawn in both the directions are giving the constant length of the bicycle. In this case, we are not able to determine in which direction the bicycle went, whether the bicycle went in anti-clockwise direction or clockwise direction. Now they move ahead in right direction. After some time, they found this track on the path. Watson asked his second question, that can a bicycle's front wheel and back wheel path ever coincide? Watson believed that this must be a unicycle path, and a bicycle can never trace such a path in which the tracks of front wheel and back wheel coincides. But Holmes suspected. Now the question is, can you drive your bike in such a way that the bike's front wheel and back wheel path coincides? At first thought, it seems that it is impossible to drive bike in such a way that it traces a path of a unicycle. As we know, Holmes is very intelligent. He came up with a very elegant solution. Now, for simplicity, we are taking the length of bicycle to be equal to 1. Now, Holmes thought that if we move bicycle's back tire on the curve phi 1, then the front tire will generate the curve phi 2. And it is equivalent to the situation that the head of the unit tangent vector drawn on the curve phi 1 and moving on the curve phi 1 is generating the curve phi 2, because as we have discussed, the bicycle's back tire and the whole frame are fixed. So they move in a direction along the motion of bicycle, but the front tire is free to rotate. So it will generate a different curve. As we can see in this animation, that the head of the unit tangent vector moving on the curve phi 1 is tracing the path of phi 2. Now, if we move our back tire on the curve phi 2, then the front tire will again generate the curve phi 3. And again, if we move our back tire on the phi 3, then the front tire will generate a curve phi 4, and so on. Repeating this process, we will get a complete path of bicycle in which the front tire path and back tire path always coincides. But as we know, the bicycle cannot take sharp turns. So the path of the bicycle must be a differentiable curve at all the points. And we know that this phi 1, phi 2, phi 3, phi 4, and so on are different curves. So the points where they meet can be the points where this path cannot be differentiable. So we have to ensure that the whole path is differentiable at the points where these different curves meet, namely 0, 1, 0, 2, 0, 3, and so on. So to avoid such problems, we will take the path of bicycle at this point to be a horizontal straight line. But now, by doing so, we have to ensure that the points where the original curves phi 1, phi 2, phi 4, etc. meet these horizontal straight lines must be differentiable. For that, we have to do some mathematical analysis. Phi n is the curve between the points 0, n minus 1 and 0, n. Now phi n can be written in terms of its previous curve. So phi n equals phi n minus 1 plus the tangent at phi n minus 1, because of the definition we have seen that at any point phi n minus 1, the tangent drawn at phi n minus 1 traces the curve phi n. So the curve phi n can be generated by two vectors. First, the position vector of point on the curve phi n minus 1, and tangent vector to this point on the curve phi n minus 1 of the length equal to the bicycle. But here we have taken the length of bicycle to be 1. So we will divide it by its magnitude, and we know how to find the tangent vector. First point represents the position vector of the point on the curve phi n minus 1, and second term represents the unit tangent vector at this point. The summation of two vectors will give the position vector of the corresponding point on the curve phi n. As you can see in this animation, any curve n can be generated by these two vectors. So our bicycle's back tire moves on the seed curve phi 1 and consequently generate the following curves phi 2, phi 3 and so on. But we have a problem. We have drawn straight lines at the points where these different curves meet, namely 0, 0, 0, 1, 0, 2, 0, 3 and so on. But the points where these straight lines meet the curves phi 1, phi 2, phi 3 and so on can be the points where the function is not differentiable. So for that, find the general solution to this problem. We'll take any curve between 0, n minus 1 to 0, n, say phi n, and we must get phi dash n because we do not want any sharp turn at any of this curve. So for that, the derivative of phi n must exist. And as we know, phi n can be expressed from previous path as the equation shown. So for phi dash n to exist, according to this equation, phi double dash n minus 1 must exist. Now, phi n minus 1 can be written as phi n minus 2 plus phi dash n minus 2 divided by phi dash n minus 2's magnitude. Now, phi double dash n minus 1 exists, phi triple dash n minus 2 must exist. And extending this logic to the seed curve, we get that n plus 1th derivative of this seed curve must exist. If this condition satisfies, then any curve phi n is differentiable within the points 0, n minus 1 and 0, if n plus 1th derivative of our seed curve exist, then any curve phi n is differentiable within the points 0, n minus 1 and 0, n. And for these 2 points, we have taken the curve to be horizontal straight line. So it is infinitely differentiable. So in general, at any point whole curve, the curve is differentiable. So there are two conditions for bicycle path to be a unicycle path. First, the seed curve by which all these curves are generated must be infinitely differentiable, because we want our n to be infinity, because we want our bicycle to be continuously moving. So our seed curve must be infinitely differentiable. And second, at all these points where these different curves meet, we must get a straight line or a curve which is differentiable. And since we are generating all our further curves with our seed curve, the starting and ending point of our seed curve is straight line. So the starting and ending point of all the further curves will also be straight line. So our seed curve will be a non-zero infinitely differentiable function, all whose derivatives are zero at the endpoints. All the curves satisfying the condition for the seed curve will be valid, and one such curve is shown here. So this is how Holmes, with his mathematical mind, solved this problem and come up with a solution that it was indeed a bicycle driver who had committed this crime. And also he found the direction in which the criminal had escaped.